Hey students, this is your Nandini Ma'am. Today we are going to read chapter number 8, Force and Laws of Motion of class 9th from the book NCERT. So let's get started. In the previous chapter, we described the motion of an object along a straight line in terms of its position, velocity, and acceleration. We saw that such a motion can be uniform or non-uniform. We have not yet discovered what causes motion. Why does the speed of an object change with time? Do all motions require a cause? If so, what is the nature of this cause? In this chapter, we shall make an attempt to quench all such curiosities. For many centuries, the problem of motion and its causes had puzzled scientists and philosophers. A ball on the ground, when given a small hit, does not move forever. Such observations suggest that rest is the natural state of an object. This remained the belief until Galileo Galilei and Isaac Newton developed an entirely different approach to understand motion. In our everyday life, we observe that some effort is required to put a stationary object into motion or to stop a moving object. We ordinarily experience this as a muscular effort and say that we must push or hit or pull on an object to change its state of motion. The concept of force is based on this push, hit, or pull. Let us now ponder about a force. What is it? In fact, no one has seen, tasted, or felt a force. However, we always see or feel the effect of a force. It can only be explained by describing what happens when a force is applied to an object. Pushing, hitting, and pulling of objects are all ways of bringing objects in motion. They move because we make a force act on them. From your studies in earlier classes, you're also familiar with the fact that a force can be used to change the magnitude of velocity of an object, that is, to make the object move faster or slower or to change its direction of motion. We also know that a force can change the shape and size of objects. Balanced and unbalanced forces. Figure 8.3 shows a wooden block on a horizontal table. Two strings X and Y are tied to the two opposite faces of the block as shown. If we apply force by pulling the string X, the block begins to move to the right. Similarly, if we pull the string Y, the block moves to the left. But if the block is pulled from both the sides with equal forces, the block will not move. Such forces are called balance forces and do not change the state of rest or of uniform motion of an object. Now, let us consider a situation in which two opposite forces of different magnitudes pull the block. In this case, the block will begin to move in the direction of the greater force. Thus, the two forces are not balanced and the unbalanced force acts in the direction the block moves. This suggests that an unbalanced force acting on an object brings it in motion. What happens when some children try to push a box on a rough floor? If they push the box with a small force, the box does not move because of friction acting in a direction opposite to the push. This friction force arises between two surfaces in contact, in this case between the bottom of the box and floor's rough surface. It balances the pushing force and therefore the box does not move. In figure 8.4b, the children push the box harder, but the box still does not move. This is because the friction force still balances the pushing force. If the children push the box harder still, the pushing force becomes bigger than the friction force. There is an unbalanced force, so the box starts moving. What happens when we ride a bicycle? When we stop pedaling, the bicycle begins to slow down. This is again because of the friction forces acting opposite to the direction of motion. In order to keep the bicycle moving, we have to start pedaling again. It thus appears that an object maintains its motion under the continuous application of an unbalanced force. However, it is quite incorrect. An object moves with a uniform velocity when the forces acting on an object are balanced and there is no net external force on it. If an unbalanced force is applied on the object, there will be a change in either in its speed or in the direction of its motion. Thus, to accelerate the motion of an object, an unbalanced force is required, and the change in its speed or in the direction of motion would continue as long as this unbalanced force is applied. However, if this force is removed completely, the object would continue to move with the velocity it has acquired till then. First law of motion. By observing the motion of objects on an inclined plane, Galileo deduced that objects move with a constant speed when no force acts on them. He observed that when a marble rolls down an inclined plane, its velocity increases. In the next chapter, you will learn that the marble falls under the unbalanced force of gravity as it rolls down and attains a definite velocity by the time it reaches the bottom. Its velocity decreases when it climbs up as shown in figure 8.5b. Figure 8.5c shows a marble resting on an ideal frictionless plane inclined on both sides. Galileo argued that when the marble is released from left, it would roll down the slope and go up on the opposite side to the same height from which it was released. If the inclinations of the planes on both sides are equal, then the marble will climb the same distance that it covered while rolling down. If the angle of inclination of the right side plane were gradually decreased, then the marble would travel further distances till it reaches the original height. If the right side plane were ultimately made horizontal, that is, the slope is reduced to zero, the marble will continue to travel forever, trying to reach the same height that it was released from. The unbalanced forces on the marble in this case are zero. It thus suggests that an unbalanced force is required to change the motion of the marble, but no net force is needed to sustain the uniform motion of the marble. In practical situations, it is difficult to achieve a zero unbalanced force. This is because of the presence of the frictional force acting opposite to the direction of motion. Thus, in practice, the marble stops after traveling some distance. The effect of the frictional force may be minimized by using a smooth marble and a smooth plane and providing a lubricant on top of the planes. Newton further studied Galileo's ideas on force and motion and presented three fundamental laws that govern the motion of objects. These three laws are known as Newton's laws of motion. The first law of motion is stated as an object remains in a state of rest or of uniform motion in a straight line unless compelled to change that state by an applied force. In other words, all objects resist a change in their state of motion. In a qualitative way, the tendency of undisturbed objects to stay at rest or to keep moving with the same velocity is called inertia. That is why the first law of motion is also known as the law of inertia. Certain experiences that we come across while traveling in a motor car can be explained on the basis of the law of inertia. We tend to remain at rest with respect to the seat until the driver applies a braking force to stop the motor car. With the application of brakes, the car slows down, but our body tends to continue in the same state of motion because of its inertia. A sudden application of brakes may thus cause injury to us by impact or collision with the panels in front. Safety belts are worn to prevent such accidents. Safety belts exert a force on our body to make the forward motion slower. An opposite experience is encountered when we are standing in a bus and the bus begins to move suddenly. Now we tend to fall backwards. This is because the sudden start of the bus brings motion to the bus as well as to our feet in contact with the floor of the bus. But the rest of our body opposes this motion because of its inertia. When a motor car makes a sharp turn at a high speed, we tend to get thrown to one side. This can again be explained on the basis of the law of inertia. We tend to continue in our straight line motion. When an unbalanced force is applied by the engine to change the direction of motion of the motor car, we slip to one side of the seat due to the inertia of our body. Mhm. The fact that a body will remain at rest unless acted upon by an unbalanced force can be illustrated through the following activities. Activity 8.1. Make a pile of similar carom coins on a table as shown in figure 8.6. Attempt a sharp horizontal hit at the bottom of the pile using another carom coin or the striker. If the hit is strong enough, the bottom coin moves out quickly. Once the lowest coin is removed, the inertia of the other coins makes them fall vertically on the table. Galileo Galilei was born on 15th February 1564 in Pisa, Italy. Galileo, right from his childhood, had interest in mathematics and natural philosophy, but his father, Vincenzo Galilei, wanted him to become a medical doctor. Accordingly, Galileo enrolled himself for a medical degree at the University of Pisa in 1581, which he never completed because of his real interest in mathematics. In 1586, he wrote his first scientific book, The Little Balance, in which he described Archimedes' method of finding the relative densities of substances using a balance. In 1589, in his series of essays, De Motu, he presented his theories about falling objects using an inclined plane to slow down the rate of descent. In 1592, he was appointed professor of mathematics at the University of Padua in the Republic of Venice. Here he continued his observations on the theory of motion and through his study of inclined planes and the pendulum, formulated the correct law for uniformly accelerated objects that the distance the object moves is proportional to the square of the time taken. Galileo was also a remarkable craftsman. He developed a series of telescopes whose optical performance was much better than those of other telescopes available during those days. Around 1640, he designed the first pendulum clock. In his book, Starry Messenger, on his astronomical discoveries, Galileo claimed to have seen mountains on the moon, the Milky Way made up of tiny stars, and four small bodies orbiting Jupiter. In his books, Discourse on Floating Bodies and Letters on the Sunspots, he disclosed his observations of sunspots. Using his own telescopes and through his observations on Saturn and Venus, Galileo argued that all the planets must orbit the Sun and not the Earth, contrary to what was believed at that time. Activity 8.2. Set a 5 rupee coin on a stiff card covering an empty glass tumbler standing on a table as shown in figure 8.7. Give the card a sharp horizontal flick with a finger. If you do it fast, then the card shoots away, allowing the coin to fall vertically into the glass tumbler due to its inertia. The inertia of the coin tries to maintain its state of rest even when the card flows off. Activity 8.3. Place a water-filled tumbler on a tray. Hold the tray and turn around as fast as you can. We observe that the water spills. Why? Observe that a groove is provided in a saucer for placing the tea cup. It prevents the cup from toppling over in case of sudden jerks. Inertia and mass. All the examples and activities given so far illustrate that there is a resistance offered by an object to change its state of motion. If it is at rest, it tends to remain at rest. If it is moving, it tends to keep moving. This property of an object is called its inertia. Do all bodies have the same inertia? We know that it is easier to push an empty box than a box full of books. Similarly, if we kick a football, it flies away. But if we kick a stone of the same size with equal force, it hardly moves. We may in fact get an injury in our foot while doing so. Similarly, in activity 8.2, instead of 5 rupees coin, if we use a 1 rupee coin, we find that a lesser force is required to perform the activity. A force that is just enough to cause a small car to pick up a large velocity will produce a negligible change in the motion of a train. This is because, in comparison to the car, the train has a much lesser tendency to change its state of rest or motion. Accordingly, we say that the train has more inertia than the cart. Clearly, heavier or more massive objects offer larger inertia. Quantitatively, the inertia of an object is measured by its mass. We may thus relate inertia and mass as follows. Inertia is the natural tendency of an object to resist a change in its state of motion or of rest. The mass of an object is a measure of its inertia. Second law of motion. The first law of motion indicates that when an unbalanced external force acts on an object, its velocity changes. That is, the object gets an acceleration. We would now like to study how the acceleration of an object depends on the force applied to it and how we measure a force. Let us recount some observations from our everyday life. During the game of table tennis, if the ball hits a player, it does not hurt him. On the other hand, when a fast moving cricket ball hits a spectator, it may hurt him. A truck at rest does not require any attention when parked along a roadside. But a moving truck, even at speeds as low as 5 meters per second, may kill a person standing in its path. A small mass, such as a bullet, may kill a person when fired from a gun. So these observations suggest that the impact produced by the objects depends on their mass and velocity. Similarly, if an object is to be accelerated, we know that a greater force is required to give a greater velocity. In other words, it appears to exist some quantity of importance that combines the object's mass and its velocity. One such property called momentum was introduced by Newton. The momentum P of an object is defined as the product of its mass m and velocity v. That is, P is equal to mv. Momentum has both direction and magnitude. Its direction is the same as that of velocity v. The SI unit of momentum is kilogram meter per second. Since the application of an unbalanced force brings a change in the velocity of the object, it is therefore clear that a force that produces a change of momentum. Let us consider a situation in which a car with a dead battery is to be pushed along a straight road to give it a speed of 1 meter per second, which is sufficient to start its engine. If one or two persons give a sudden push to it, it hardly starts. But a continuous push over some time results in a gradual acceleration of the car to this speed. It means that the change of momentum of the car is not only determined by the magnitude of the force, but also by the time during which the force is exerted. It may then also be concluded that the force necessary to change the momentum of an object depends on the time rate at which the momentum is changed. The second law of motion states that the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of force. Mathematical formulation of second law of motion. Suppose an object of mass m is moving along a straight line with an initial velocity u. It is uniformly accelerated to velocity v in time t by the application of a constant force F throughout the time t. The initial and final momentum of the object will be P1 is equal to mu and P2 is equal to mv respectively. So the change in momentum will be P2 minus P1, which is mv minus mu, and m after taking common will come out of the bracket, leaving v minus u. The rate of change of momentum is m into v minus u over t. So F is the applied force, which is directly proportional to m into v minus u over t, and changing the sign of proportionality, we have F is equal to km into v minus u over t, and F is equal to kma, as a is equal to v minus u by t, which is the acceleration and is the rate of change of velocity. The quantity k is a constant of proportionality. The SI units of mass and acceleration are kg and meter per second square respectively. The unit of force is so chosen that the value of the constant k becomes 1. For this, 1 unit of force is defined as the amount that produces an acceleration of 1 meter per second square in an object of 1 kg mass. So now the formula becomes F is equal to ma. The unit of force is kg meter per second square or Newton, which has the symbol N. The second law of motion gives us a method to measure the force acting on an object as a product of its mass and acceleration. The second law of motion is often seen in action in our everyday life. Have you noticed that while catching a fast moving cricket ball, a fielder in the ground gradually pulls his hands backwards with the moving ball? In doing so, the fielder increases the time during which the high velocity of the moving ball decreases to zero. Thus, the acceleration of the ball is decreased, and therefore, the impact of catching the fast moving ball is also reduced. If the ball is stopped suddenly, then its high velocity decreases to zero in a very short interval of time. Thus, the rate of change of momentum of the ball will be large. Therefore, a large force would have to be applied for holding the catch that may hurt the palm of the fielder. In a high jump athletic event, the athletes are made to fall either on a cushioned bed or on a sand bed. This is to increase the time of the athlete's fall to stop after making the jump. This decreases the rate of change of momentum and hence the force. Try to ponder how a karate player breaks a slab of ice with a single blow. The first law of motion can be mathematically stated from the mathematical expression for the second law of motion. F is equal to ma, F is equal to m into v minus u by t, and F into t is equal to mv minus nu. That is, when F is 0, v is equal to u for whatever time t is taken. This means that the object will continue moving with uniform velocity u throughout the time t. If u is 0, then v will also be 0. That is, the object will remain at rest. Third law of motion. The first two laws of motion tell us how an applied force changes the motion and provide us with the method of determining the force. The third law of motion states that when one object exerts a force on another object, the second object instantaneously exerts a force back on the first. These two forces are always equal in magnitude but opposite in direction. These forces act on different objects and never on the same object. In the game of football, sometimes we, while looking at the football and trying to kick it with a greater force, collide with the player of the opposite team. Both feel hurt because each applies a force to the other. In other words, there is a pair of forces and not just one force. The two opposing forces are also known as action and reaction forces. Let us consider two spring balances connected together as shown in figure 8.10. The fixed end of the balance B is attached with a rigid support like a wall. When a force is applied through the free end of the spring balance A, it is observed that both the spring balances show the same readings on their scales. It means that the force exerted by spring balance A on balance B is equal but opposite in direction to the force exerted by the balance B on balance A. Any of these two forces can be called as action and the other as reaction. This gives us an alternative statement of the third law of motion, that is, to every action there is an equal and opposite reaction. However, it must be remembered that the action and reaction always act on two different bodies or objects simultaneously. Suppose you are standing at rest and intend to walking on a road. You must accelerate, and this requires a force in accordance with the second law of motion. Which is this force? Is it the muscular force you exert on the road? Is it in the direction we intend to move? No. You push the road below backwards. The road exerts an equal and opposite force on your feet to make you move forward. It is important to note that even though the action and reaction forces are always equal in magnitude, these forces may not produce accelerations of equal magnitudes. This is because each force acts on a different object that may have a different mass. When a gun is fired, it exerts a forward force on the bullet. The bullet exerts an equal and opposite force on the gun. This results in the recoil of the gun. Since the gun has a much greater mass than the bullet, the acceleration of the gun is much less than the acceleration of the bullet. The third law of motion can also be illustrated when a sailor jumps out of a rowing boat. As the sailor jumps forward, the force on the boat moves it backwards. Activity 8.4. Request two children to stand on two separate carts as shown in figure 8.1. Give them a bag full of sand or some other heavy object. Ask them to play a game of catch with the box. Does each of them experience an instantaneous force as a result of throwing the sandbag? You can paint a white line on the cart wheels to observe the motion of the two carts when the children throw the bag towards each other. Now place two children on one cart and one on another cart. The second law of motion can be seen as this arrangement would show different accelerations for the same force. The cart shown in this activity can be constructed by using a 12 mm or 18 mm thick plywood board of about 50 cm into 100 cm with two pairs of hard ball-bearing wheels. Skateboards are not as effective because it is difficult to maintain straight line motion. What you have learned. First law of motion. An object continues to be in a state of rest or of uniform motion along a straight line unless acted upon by an unbalanced force. The natural tendency of objects to resist a change in its state of rest or of uniform motion is called inertia. The mass of an object is the measure of its inertia. Its SI unit is kilogram. Force of friction always opposes motion of objects. Second law of motion. The rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of the force. The SI unit of force is kg meter per second square. This is also known as Newton and is represented by the symbol N. A force of 1 Newton produces an acceleration of 1 meter per second square on an object of mass 1 kg. The momentum of an object is the product of its mass and velocity and has the same direction as that of the velocity. Its SI unit is kg meter per second. Third law of motion. To every action, there is an equal and opposite reaction, and they act on two different bodies. And this was the chapter number 8. And do read it once again, listen to the recording, and study well. Best wishes.